This is the third problem in the mesh analysis using KVL and KCL series, and this is our problem. We have two current sources and one voltage source. We have a 10-volt source on the left, a 4-amp current source on top, and a 5-amp current source down the middle. So we're going to solve this in the same way that we normally do by drawing the mesh current loops around each mesh. So I'm starting on the left of the top current source, and I'm putting a minus sign. It's a minus as it enters the current source and a plus as it exits. And I'm going clockwise around this particular mesh loop. As I enter a resistor, I place a plus sign. As I exit, a minus sign. And I'm continuing to do this through R2 and R1. Again, just clockwise. It's very simple. There's nothing complicated here. It's just about getting the polarity right. So this is our mesh current for our mesh current 1, which is 4 amps, and that's given by the current source. Now I'm going to the bottom left-hand corner, and this will be the mesh current for mesh 2. I'm putting a plus sign as the mesh current enters R1. Notice again, that's the opposite of the mesh current I1. The polarity is opposite, so it really depends on your frame of reference. So when you're making the simultaneous equations to solve the system, it's really the frame of reference that you're looking at that determines whether you're going to be adding or subtracting currents. As you'll see here with the mesh current 3, which I'm drawing now, it's going counterclockwise, and there will be two currents entering R2, which is going to be I1 and I2, and they'll both be in the same direction. So you're going to see that shortly as we go through these problems. And once again, there's no really need to worry about the voltage across the current source at the moment, but that is something we do have to find. It's not just given like it is with the DC sources. So our current through I1 is going to be 4 amps. That's our mesh current I1. Notice that the current source I2 is going to be a sum. So that's labeled I2 on the diagram, but it will be I2 and I3. So the sum of the mesh currents I2 and I3 is equal to 5 amps DC. Okay, so the next thing we want to do is find the equations for each mesh section. So provided that we've written the polarity correctly on our mesh currents, this shouldn't be too hard. So we have minus VS1. VS1 is the current source. It's going to be minus VS1 plus 25, I1 plus I3. So we're adding those two currents together. So from the frame of reference of I1 in the first mesh current, I3 is going in the same direction. So that's why we're adding those together. As opposed to if you look at R1, which is 10 ohms, we have I1 minus I2. So from your reference frame of the first mesh current, we're subtracting I2 because it's going against the direction. And that situation reverses in loop 2. We have minus 10 plus 10 I2 minus I1 minus VS2. VS2 is the voltage across the current source. So we're in the reference frame of loop 2. So we are subtracting I1 from I2 in that instance. The voltage across the current source is going to be the same in loop 2 and loop 3. So that polarity is going to be the same. So we have three equations from 3 loops here, and we have more than 3 unknowns at this point. Or we may. Let's find out. We have I1, I2, and I3, and as well as the voltage across S1 and the voltage across the current source S2. So we already know that I1 is 4 amps, and we know that I2 is 5 minus I3. because the sum of I2 and I3 is 5 amps. So we have 3 unknowns and we have 3 variables. So we can solve the system of equations. So that is important to know before you embark on solving systems of equations. You want to know if you can even solve the system. So we're writing the equations out once again. 35I1 minus 10I2 plus 25I3 is equal to the voltage drop across the current source. The first current source, Vs1. From loop 2 we find that we have minus 10I1 plus I2 is equal to the voltage drop across the current source 2 plus 10. And from loop 3 we have 25I1 plus 75I3 is equal to Vs2, which is the voltage drop across current source 2. So we're just solving the system of equations by cancellation. So we're eliminating one of the variables, and what we're going to end up with is what looks like two equations and 2 unknowns, but we already know what I1 is. We already know that is 4 amps, so we end up solving for I3, and that's what we're doing now. Vs2 cancels out after multiplying by minus 1. The loop 3 equation was multiplied by minus 1, so we're able to subtract that out and substitute in I1, which is again 4 amps. And we can solve for I3. So I3 is equal to minus 1.176 amps. So what that means is the current is actually going in the other direction than what we had originally drawn on the diagram. So that's I3. Solving for I2, we get 6.176 amps, and of course we know I1 is 4. So once again, I3 is going in the opposite direction. It's going clockwise through that loop, and that's why we have the minus sign there. So there's no reason to be alarmed. This will change the polarity of some of the voltage drops across the components, but we can, in fact, just keep the sign in there for now, and the rest of the circuit will add up correctly. So the voltage drop across R3 is minus 58.8 volts, and that's with the polarity that we have indicated on the diagram, which means that the north side of R3 is really positive. So if you want to invert that, you'll get the less complicated answer. So we can solve for the voltage drop across R3, R2, and R1. And using that information, we can find the voltage drops across the 2 current sources in the circuit. So from loop 1, we find the voltage drop across the current source 1 is going to be 35I1 minus 10I2 plus 25I3. And just substituting in the currents, we can solve, since we know the currents already. So we have 48.8 volts across the current source, first current source, and from loop 2 we can find the voltage drop. Well, actually loop 3 is a little easier. We can find the voltage drop across the second current source, which comes out to 11.8 volts. So we can see how it looks against the simulation. This is the results we get from the PSpice simulation. We can see it is pretty close to what was calculated by hand, and that's pretty good. It's always a good idea to check your results against a simulation. In this case, PSpice, and the results match pretty closely to what we've done here. So it's always good practice to try your own problems, make up your own problems, check them against a simulator. Anyway, thanks for watching. Feel free to try problem number 4 if you'd like. Maybe I'll see you there.